Hello everyone. In this video, we discuss parametric regression models, including linear regression. Linear regression is one of the simplest yet most fundamental machine learning models. Despite its simplicity, it serves as the backbone of many complex models due to its core principle, the weighted sum of input features. This concept extends to neural networks and other advanced models, making linear regression an essential foundation in machine learning. Beyond just fitting a straight line to data, linear regression requires a strong understanding of its underlying assumptions. These assumptions guide when and how the model performs well, ensuring its reliability in practical applications. Another crucial aspect of this lecture is expressing data transformations in compact and efficient forms using vectors and matrices. This not only simplifies computations, but also provides a bridge to more advanced techniques in machine learning and AI. Recall that we have this general framework for machine learning models where we provide inputs or features that they go through some data transformation layers. In this case, because we are working with linear regression, this is the weighted sum or linear combination of inputs that will give us some predicted outputs. And then one thing that we have to discuss is the choice of loss or cost function that measures the discrepancy between true and predicted outputs. And then we discuss how we can find the optimal parameters or weights of this data transformation using two techniques. One is a more traditional approach known as the normal equation, and then the second approach is gradient descent, which is a very important optimization technique in the modern machine learning and AI landscape, which empowers most deep learning models. And at the end of this module, we will focus on nonlinear extension of linear models and also a very important technique known as regularization, which can also help us to better find machine learning models that can capture intrinsic data structures. To get us started, let's recall some of the assumptions that we have to make for a very simple linear regression case. In this case, we are assuming that the input features or inputs that we have, it's only one dimensional, meaning that in this case, we have one scalar input and one scalar output, which we can show this using these input-output pairs. The small n here, this is used for indexing in the subscript, and n goes from 1 to uppercase n, and therefore the uppercase n is the number of data points or observations that we have. Something that I would like to emphasize here is that when we want to train a model using this data is fixed and given to us. Therefore, you can think of xn's andyn's here as being constants because we are not really optimizing anything over these input-output pairs, and these are just given to us. However, we are making this assumption that the predicted output for a given input x, if we want, we can also use x subscript n here, but for simplicity, I usually don't use subscripts when we're talking about the general assumption that we make because this works for any x, including xn, is theta 0 plus theta 1 x. And this is what is known as, in this case, the equation of a line where we have a slope and intercept. Therefore, the entire goal here is to find the optimal values of theta 0 and theta 1 such that predicted outputs are as close as possible to true outputs, which they come from our training data. And we can solve this problem by setting up an optimization problem where we use a loss function. And in this case, the loss function is this quadratic form. So what we do is we have the true output yn, and we have the predicted output coming from our linear model, which is f of xn, and we can subtract these two to find the residual or prediction error, and we can raise this to the power of 2 to make sure that they're all positives. Also, in one of the homework assignments, we showed that this loss function comes from the maximum likelihood estimation framework. So this means that this optimization problem that we have here to minimize the value of this term over theta 0 and theta 1 is actually equivalent to the maximum likelihood estimations of these two unknown parameters, theta 0 and theta 1. Overall, this loss function is known as also mean squared error or MSE because we sum all these prediction errors and we also divide these by the total number of data points, which is this uppercase N. So with this motivation in mind, this is also called mean squared error. Something to keep in mind is that this constant that we use right before the summation does not change the optimal solution of theta 0 and theta 1 because in this case we are not necessarily looking at the minimum value of this loss function. We are actually looking at the minimizers, meaning that what values of theta 0 and theta 1 will lead to the minimum value of this loss function. And in this case, if we multiply these objective function by any positive constant, we are not changing the problem in the sense that the minimizers are the same. And we can always multiply this by any constants that we want as long as they are non-negative. In order to solve this problem, one thing that we have to keep in mind is that in this case, we have two optimization variables, theta 0 and theta 1. Therefore, when we want to use the principles of solving optimization problems, meaning finding derivatives and setting them equal to 0, we have to take this into consideration that we actually have to once find the partial derivative with respect to theta 0, meaning that everything else is constant or fixed, except for theta 0, and then second time we have to find the partial derivative with respect to theta 1, and then we can set them equal to 0. Next, I'm going to show you actually how you can derive these equations here and in a couple of slides. Okay, so just to recap, remember that this is the optimization problem that we have. So we want to minimize this mean squared error where we have these two optimization variables, theta 0 and theta 1. And the goal here really is to find these minimizers theta 0 and theta 1. So for what values of theta 0 and theta 1, this loss or cost function achieves its minimum value. And if you're wondering, so this function f of xn here, this is a function of theta 0 and theta 1. That's where here we have to take this into consideration that this f is actually a function of theta 0 and theta 1. And again, I'd like to emphasize that in this case, these xn and yn's are fixed and given to us. So this is part of our training data that provided to us. And also this is the model assumption that we have. Okay, so in order to find partial derivatives, let's just substitute here this theta 0 plus theta 1 xn. We also have a negative sign here. So for that reason, this would be negative theta 0 minus theta 1 xn. And if you take the partial derivative of this with respect to theta 0, remember that since derivative is a linear operator and you have a summation here, this means that you can find the derivative of the terms inside this summation. And for now, think of these as like chain rule, and let's call this z or any other variable that you want. So if you take the derivative of z squared with respect to z, that's just 2 times z. 2 is here. We can take this out of the summation. And this is that variable z that we have. Now, the only thing that remains is that we have to find the partial derivative of z with respect to theta 0 according to the chain rule. And this is the part that you can see that in this case, everything except for theta 0 is constant. So this whole term here is constant since we are finding the partial derivative with respect to theta 0. And the only thing really remains here is this negative theta 0. And if we take the partial derivative with respect to theta 0, then we get negative 1. And this is something that also we can take out of the summation. You can see we get negative 2 over n, and then this summation from 1 to n of yn minus theta 0 minus theta 1 xn. And remember that we can put this back again in terms of f of xn. I can write this as negative theta 0 plus theta 1 xn. And this is exactly the function f of xn. And if we want to, we can also put this negative sign back in front of this summation. So in this case, the final result is 2 over n, summation from 1 to n of the predicted values minus true values. So that's something important to remember. So these are our predicted values. Yns are our true values. And this is the partial derivative with respect to theta 0. We can do a similar analysis for partial derivative with respect to theta 1. I will not repeat all the steps, but you can see that easily. The main difference here, if I use a different color, is in this case, where now we have to find the partial derivative of this with respect to theta 1 instead of theta 0. And in that case, when we take the partial derivative with respect to theta 1, the result is negative xn. And you can see this being the case here, where we have this xn, and the negative sign is already applied to this part, where we originally had yn minus f of xn, but because we multiplied that by negative 1, now we have f of xn minus yn. Definitely something that I would recommend you to replicate this step to make sure that you fully understand this. But you can see that the main difference is that in the previous case, we had here 1, but now we have xn when we have partial derivative with respect to theta 1. One of the most important things that we have to remember in this case is that this loss function that we have is function of two variables, theta 0 and theta 1. These are the things that we want to optimize over. And since now we have a vector valued function, we can put all these partial derivatives into a vector, which is called gradient. And this is the notation that we're going to use. So gradient of this loss function with respect to theta 0 and theta 1 is this vector where the first element is partial derivative with respect to theta 0. The second element is partial derivative with respect to theta 1. And from here, we can just substitute what we found, right? So the first one is this summation fxn minus yn times 1. We can add it if we want. And then for the second one, we get f of xn minus yn times xn. So right now, it seems that we are done, but something that is very important in machine learning and AI in general, is to be able to write these types of expressions in very compact forms. And in compact forms, I mean in terms of vectors and matrices or higher dimensional tensors and arrays. And in this case, in particular, we want to avoid the summation because summations are usually implemented naively using for loops, and that's something that can be super slow. So how can we do this? In order to write this expression here for the gradient in simplified or compact form, let's define a few vectors and matrices here. We define a matrix X, which we can call this like the data matrix. We can also call this feature matrix, which is of size n by 2. So n is the number of data points we have in our training set, and 2 is the number of columns. And you can see that we have a column of all ones, and then we have a column of these actual scalar features that we have for each observation. And if you're wondering where this one comes from, it has to do something with this one that we have here, and we'll explain this. And then you have here a target or output vector, which contains all the corresponding output for these inputs, and then a parameter or weight vector. So again, remember that in this case, x and y are given to us. What we're really trying to find is what should be this vector theta. And one nice thing you will see that soon is that now if we have even a higher dimensional problem, meaning that each input have multiple features, we can use the same type of notation, except the fact that X will have more columns. And that's the only major difference on the data side. And on the theta parameter that we will have theta 0, theta 1, theta 2, theta 3, corresponding to the new features that we have for each data point. So with this in mind, can we find a vector of all predictions? So what are these predicted values that we have? So we know that for data point 1 is theta 0 plus theta 1 x1, theta 0 plus theta 1 x2 for the predicted value for x2. And for xn, we have theta 0 plus theta 1 xn. There's a pattern here, right? So it looks like this theta 0 and theta 1, which is a vector here, is multiplied in the first case, or I would say we are finding the dot product between this vector theta 0 and theta 1, and another vector which is 1 and x1. Why? That's the idea behind matrix vector multiplication. You can think of the result of these as finding the dot product or inner product between the first row of this X matrix and this column vector theta 0 and theta 1. The same thing happens with this one, right? So with the second element here, you can see that we have theta 0 and theta 1, which is we have here. And then we have 1 and x2, which is here. So this means that if I multiply my data matrix or input matrix by theta, so this is matrix vector multiplication, we find a vector that contains all predicted values. Now, since one part of this whole process is to find the difference or the residual, which is the difference between predicted and true values, now we can subtract this x times theta by y, which is the vector of all true outputs, and this will give me a vector that I have all the residuals, right? Residual for data point 1, residual for data point 2, etc. up to n. And just to make sure this is uppercase n here. So then remember that x theta minus y is an n-dimensional vector which contains all these residuals. Now we go to the next and final step here. So we have this x theta minus y, which is the vector of all residuals. And then we had, if you remember originally this matrix X, which was of size n by 2. If we find X transpose, meaning that we switch rows and columns, so now we will have a row of all ones and a row of all features x1 through xn. And if you can remember this idea of matrix vector multiplication, so this means that here the result will have only two elements because this is 2 by 1 and n by 1. So these two neighboring dimensions match and the result is 2 by 1. And you can see that the first element is going to be this dot product or inner products between 1 and the corresponding residual, which is this summation. And for the second one, the only difference is that now we have the corresponding xn element. And this goes from summation from n to n. And we are done. So what we really showed here, so this is more like a reverse engineering approach, but we showed that this gradient, which is very important because it contains information about all partial derivatives with respect to the unknowns, can be written as 2 over n times x transpose x theta minus y. And the reason at the end I multiply everything by 2 over n, that's because that's exactly what we had in our gradient. And we can do this. Remember, again, like, once you work with these types of multiplications, you can multiply both sides by any scalar that we want. So 2 over n is just a constant that we use to multiply both sides. And you can see that we use this idea here that this can be written in the form of dot product or inner product, which if we put everything together and we stack these rows and columns here, you can see that we can write this as matrix vector multiplication. So overall, for the case of univariate linear regression, with the way that we define matrix X and vector Y and vector theta, this is our gradient. So now in order to solve this optimization problem that we had, which was finding values of theta 0 and theta 1 that minimize this objective function, the very first thing we want to do is to set this gradient equal to 0. So this is equivalent to setting all those partial derivatives equal to 0 to find the optimal solution. And if we do this, so that's what exactly we do in the first line. So since obviously here we can multiply both sides by n over 2, we can get rid of this constant. That's the first thing we do. Remember, when you do matrix multiplication, you always have to respect the order. So this means that in this case, we have x transpose x theta minus x transpose y equal to 0, which is what we have here. And then we can send x transpose y to the other side and solve for theta. And we can do this by multiplying both sides by the inverse of x transpose x. And remember, again, when you do this from the left side, this multiplication, you need to remember that you have to do this on the left side here too. So in this case, these two, they cancel. So we get identity matrix, which is equivalent to 1. And this means that the optimal solution is x transpose x inverse x transpose y. So the idea was, well, what should be the optimal transformation, right? Because remember, again, the workflow that we have, we set x, this x gets multiplied by theta 0 and theta 1. So this gives us theta 0 plus theta 1x. This is our predicted values. The true value is y. And then we have the loss function, which is in the form of mean squared error here. And then we have to find the optimal values of theta 0 and theta 1. And in this case, we have a nice closed form solution since this is a very simple linear model. You will see that later on, this is usually not the case, and we have to use gradient descent. But for now, we have a solution in this closed form structure. And one thing I want to emphasize here is that once you find the optimal values of theta 0 and theta 1 according to your training data, meaning that you're done with the training phase, now you can actually use this optimal value to make predictions. And remember, in order to make predictions, what you really need is the features or inputs for your test data. And in this case, the test data that you have is in the form of, let's say, n test rows, right? Because the number of testing data points can be different from the number of training data points. And now we have this one, which is something that we always add, and then the feature for that corresponding test data point. So this is the feature one of the first test data point up to the last one that we have. So this is also of size n test by 2. And in order to find this linear combination between theta 0 and theta 1 and these features, you can do this in one step by multiplying this x matrix by this vector theta. And this is just a simple matrix vector multiplication. And in one operation, it will give you predicted values for all the testing data points. Okay, going back to the Jupyter notebook, you'll see that we found these partial derivatives with respect to theta 0 and theta 1. Then we discussed the idea of gradient, which is used to extend the notion of derivatives to handle vector argument functions that we have here. And since we have only two parameters here, theta 0 and theta 1, this means that this gradient vector has only two elements too. And then we talk about the compact form of the gradient in this case, which is in the form of the data matrix, vector theta, and in the target or output vector. And we showed you all these steps. And the basic idea is just matrix vector multiplication, which can be viewed as the dot product between each row and the corresponding vector that we have in front. Something I mentioned in the just the note that we had was that, well, we can actually solve this problem for theta. This is a system of linear equations by multiplying both sides by x transpose x inverse. So to get rid of this matrix that we have here, so then we can find theta as x transpose x inverse x transpose y. But this is not the only way to solve this problem. So this corresponds to a class of problem known as least squares. And in fact, in Python, there is a way to solve this problem exactly by just providing this matrix that I just call it A for simplicity and this vector B. And as long as you provide these two, you can find the solution. In order to show you this, let's look at the real world example. Let's look at the life satisfaction data. This is a data set that has two main columns. GDP per capita, and then a life satisfaction score. So here the goal is that we want to think of this GDP value or score as the input or the X variable that we had. And then life satisfaction is the output or Y. So the goal is that now we be able to train a linear regression model such that if in the future, if we have a new country with a given GDP, we are able to predict the corresponding life satisfaction score. Obviously, you can get some information about these. Here we have 27 samples of data points, and you can see that we have three columns. You are not going to use the country information because this is in the form of text. It's not numerical, so we're mainly going to use GDP and life satisfaction. And that's exactly what we do here. So we're going to use this column of data frame, convert this to a NumPy array, and then we have this other column for the output, and we convert this to a NumPy array. So you can see immediately that now we have this like X array and Y, and we have to one thing that is very important here. So remember in the theoretical analysis that we did, we always assume that the first column of X, we have an array of all ones. So far we do not have this, right? Because if I show you what's inside X, you can see these are the values of actually GDP. So I need to convert these to a two-dimensional array or matrix X where we add this column of all ones. And thanks to NumPy, this is really easy to do using this function that we define here, where we use this method called np.concatenate. And the way this works, we create a tuple, as you can see because of these square brackets, where the first element here is array of all ones, and the number of rows is the same as the number of rows in X. So in this case, that's why we use x.shape 0. So this will give us the number of rows in this X that we have. And then we also assume that here we have one column. So this will give you a column vector where we have all ones. And then we're going to also reshape this X that we have by using this X dot reshape negative 1 and 1. So what this does, I can show you this one here. When you say X dot reshape negative 1 and 1, this means that get this one-dimensional array here. Make sure it has one column, but I don't want to exactly specify the number of rows because once you have one dimension, you can always find the other dimension. And in this case, NumPy is smart enough to know that, well, this negative one should be actually 27. So if I do this, so you can see that now this looks very much like what we expect, like a column vector where we have in each row one value of GDP. And now you have this vector of all ones that I can show you that too. And then we combine them together. So you can see that that's the vector of all ones. So if we run this and add these columns, you can see that this X concatenated exactly has the same format as what we discussed. Is n by 2, where n is here 27, and the first column is all ones, and then the second column are the GDP values. And here I have some extra information for you if you want to know exactly how np.concatenate works. So with this in mind, so let's go back to what we had here. Here we have A, which is X transpose X, and we can do this in NumPy using matrix multiplication. And then we have X transpose time Y as being B, which is on the right side of this equation. So in this case, you can see that we have X transpose X, and remember this X should be the one that is concatenated with the vector of all ones. And then B is just X transpose Y. And here is the method that I just mentioned. So inside NumPy, there is a linear algebra module, that's this linalg. And inside this, we have this least square solver. So you can see here, we provide A and B. Also, once, if you're familiar with linear algebra perspectives of this, you have to be careful with some of the singular values when you want to solve this problem. So that's what this part is about, but it's like one of those things that you do not necessarily have to specify. The main input arguments here are A and B. And this should give us that two-dimensional vector theta when you solve it. And according to this, the solution is 3.7 for theta 0, and then theta 1, which is the slope, is in the order of 10 to the negative 5. Which makes sense because if you look at these values that we have, they are in the order of 10 to the power of 4. So therefore, theta 1 should be a small such that when you do this multiplication between features and parameters, then you get life satisfaction scores that are in sort of like, I do believe in the range of like less than 10 from 1 to 10. And in order to make sure that your model works very well, so you can, once you find the theta, so like here we find that, you can do this x times theta. So in this case, you get predicted values. And what we do, because since this is a linear regression model, we only need 2 points on this linear regression model to be able to plot it. And we can look at the minimum and maximum values that we have for x. These are those GDP values from the data set. We need to make sure that we add that column of all ones. And once we do that, we can just do a simple matrix vector multiplication using this function f, and we can plot this regression line that we have here. So here is the result as we see, like you can see that here the GDP values are roughly speaking from 25,000 to 60,000. And given theta 0 and theta 1, which is the intercept and slope, this is what our model, this dotted line is what our model predicts. So this means that if you have a country, let's say with GDP 45,000, then we can look at the corresponding value here, which is shy of 7, probably 6.8 or something like that. And that would be our predicted value. And we can easily extend this to the case that we have more than one input feature, thanks to the flexibility provided by gradients. So you can see that in this case, we assume that xn is actually a vector because it's a bold-faced letter. And it's a vector of that has d elements or d dimensions. In this case, we have theta 0, theta 1, up to theta d. And therefore, we can write this as theta 0, which is our intercept, plus theta transpose x, or the dot product or inner product between the vector theta and the vector x, which is the input feature. And the elements of this theta is, we can think of these as weights or regression coefficients, and theta 0 is the intercept. And we can even write this in a little bit more compact form if we assume that this x vector is concatenated by this constant 1. That's what you just saw before in our univariate analysis too. And in this case, you can see that we get a d plus 1 dimensional feature vector. And then we have d plus 1 dimensional parameter or weight vector. And therefore, the predicted value, this f here, is simply the dot product between theta and x. The only difference here is that we absorb theta 0 into theta vector, and also that constant 1, and therefore we can always assume that we have a feature that always equals 1, and that gives us that interceptor. And everything else works the same way, right? So in terms of like the loss function and defining MSE or mean squared error, we have the same thing. We have the average of the sum of, we have the average, which is the sum of residuals when we raise them to the power of 2, and then divided by the total number of data points. And since we already talked about this, we can find all the predicted values as a vector bound by multiplying x and theta, and y contains all the true outputs. So in this case, we get a vector which each element is one residual for one of the data points. And since the Euclidean norm square of a vector is the sum of the square of the elements, this is a better way to summarize these or rewrite this loss function that we have here. So this means that we can assume that this y is the vector of all true outputs, and x theta is all the predicted outputs. We subtract them, so we find in one operation all residuals, and now we can find the norm of this vector, raise this to the power of 2, and then divide that by n. And remember, in this case, x is a matrix where each row contains one data point. That's why we have n rows. And each column is one feature. And since here we technically have d plus 1 features, this is of size n by d plus 1. And theta is d plus 1 dimensional vector, and y also has n elements here. So this means that multiplying x by theta gives us a vector of size n by 1, or n, since here we are talking about column vectors, and then we have this target or output vector y, which is also size n, and we can subtract them. And then the goal is to find the minimizers of this loss function where we have d plus 1 of them. And in this case, as we explained in the notes, you can find a closed form solution because it's a very simple linear model. And after you find the gradient, which is exactly what we have, 2 over n x transpose times x theta minus y, you set this equal to 0, and we showed multiple steps how we can get this solution. So therefore, for linear regression, now we understand the model assumption, how to define a loss function. That's like the general form that we have. And once you define a loss function, you need to find the gradient, which is relatively straightforward here. And then we can set this gradient equal to 0 to find the optimal solutions.